Hello and welcome to Yeyu Lab. In our previous videos, we've explored the capabilities of the Gemini 2.0 multimodal live API, including real-time interactions through text, voice, and camera, along with the screen sharing. It's happy to see those tutorials has been helpful to the community and developers to start their own projects. However, there is still a critical issue that prevents the real-world application implementation, which is the inability to provide both real-time text and audio responses concurrently. Even the response modality parameter in the library is allowed to be set as a list of audio plus text, but actually that setting is not working as expected with only an error throughout. As I've mentioned before, the Gemini multimodal live API is still in the early stage with experimental status, so whether or when such an issue will be handled as a requirement is still unknown. As a channel of development enthusiasm, we should not wait for the official support, but instead we should find a way to make it work. As a reminder, Google AI Studio's Stream Real-Time section lets you to experience the multimodal nature of Gemini 2.0 by getting both text and audio output. And it's quite smooth when text transcription displays in the proper rhythm with the audio stream. Let's see that. Share your screen. Find a paper that we want to share. Please look at the screen.
Okay, I'm looking at the screen. It seems like the paper is titled Don't Do RAG, when cache augmented generation is all you need for knowledge tasks. Would you like me to tell you anything specific about it?
Yeah, just simply explain the diagram.
Sure, I can explain the diagram. It appears to show a comparison between two workflows, traditional RAG and the paper's proposed CAG workflow. The traditional RAG workflow is shown in the upper section, while the CAG is shown in the lower section. Would you like me to go into more detail about either of the workflows?
So you can see that Google has definitely used some integrated components to make this text and audio display work, but they have not released it for public usage yet. So in this video, we will address the limitation with a new transcription approach, enhance the multimodality by providing both readable transcriptions and audio feedback to implement the real-time screen sharing assistant. And this video will focus more on the core implementation of voice text output, especially the backend server. So the entire screen sharing process is implemented with Gemini 2.0 multimodal live API in our previous video. So if you haven't seen it yet and want to know especially the details of the front-end design, please check it out, or you can just watch this video to see how the key features of text audio improvement in the backend server and copy the front-end code from my GitHub repository in the description below. First, let's take a look at the overall structure and data flow of this project. The application uses two Gemini models in a streamlined process. First, the client sends visual and audio inputs to the server. The server then uses Gemini 2.0 Flash model for real-time audio streaming generation. Next, the server uses that output to transcribe this audio output into text using Gemini 1.5 Flash 8B model. And finally, the server sends both audio and text data back to the client for user's output. This ensures the user receives both the audio and its transcript for a complete multimodal experience. The reason why we use two different models is that Gemini 2.0 Flash model is designed for multimodal audio streaming, while the Gemini 1.5 Flash 8B model is much more suitable for transcription tasks because it accepts audio input like other Gemini models, but provides highest generation speed and the lowest latency. Even its intelligence is not as high as the Gemini 2.0 Flash model, but it's enough for speech to text conversion. And the most important thing is that it's super cheap. By using two models, we can ensure that the audio is processed efficiently and the transcription is fast. Now let's take a look at the server code. First, as always, we need to install the Gemini's packages, but this time you should be very careful to install both the production Gemini API, Google Generative AI, and the experimental Gemini Live API, Google Gen AI packages. The Google Generative AI is for Gemini 1.5 Flash model for text generation of audio transcription. The Google Gen AI package is for Gemini 2.0 Flash model for multimodal live generation, as what we have done before. And also, don't forget to install the WebSockets and PyDub, which is for audio processing. And also, you should install the FFmpeg software to enable the core processing of the audio conversions in your computer. Based on the type of the OS, you should find a way to install it. Okay, so after installation, you need to import those packages, load the API key from Google AI Studio, and also the key need to be imported into generative configure method to enable the text generation from the Google Generative AI. And define the two models. One model is Gemini 2.0 Flash EXP, and the other transcription model, we use Gemini 1.5 Flash 8B. And then define the client object for the multimodal live generation, and use the API version v1 alpha. And this is the configuration for Google Gen AI object. And we will use this client to do the WebSockets connection and the data exchange with the Gemini 2.0 multimodal live API. Then at the bottom of the code, we call WebSocket serve method function to establish a server on a specified port. And this server is the bridge between the client we designed with HTML and JavaScript and the Gemini 2.0 multimodal live API. Each WebSocket connection through the local host and port 9083 from our front-end client triggers the handler function Gemini session handler, and we will explain it now. In the Gemini session handler function, we first receive the client's configuration message, and then we use the client AIO live connect method to connect to the Gemini 2.0 multimodal live API. This method returns a session object that we will use to send and receive data. This part has no difference from the previous video, and including the send to Gemini function, which manages the sending of the messages from the client WebSocket to the Gemini API, and the messages include the user's voice audio data and a screen sharing image data. Okay, and the receive from Gemini function, which was originally used to listen to responses from the Gemini API and unpack text and audio data to be sent to the client, now has additional steps. Here, when the audio data comes, we accumulate all audio data received into a session audio data list. Once the turn complete flag is received, the server will call transcribe audio function and send the transcribe text back to the client. And we also clean the session audio data list for the next round. The turn complete flag indicates the end of the current model response because the audio understanding of the Gemini 1.5 model uses the API that is block API working synchronously. So the server needs to wait for the response to be complete before sending it to the client. That will cause the latency between the audio playback and text output. But that's okay for most cases. And as we have done before, the two tasks sent to Gemini and received from Gemini has been created by the async IO method and get them working parallel. The key part of this demo is the transcribe audio function. Let's take a close look at it. The function receives the accumulate audio data. First, it converts the PCM audio into the base 64 encoded MP3 format, and then use the Gemini 1.5 model to generate a transcription using the generate content method with our system prompt that tell the model to generate a transcript for the speech. Please do not include any other text in the response. If you cannot hear the speech, please only say not recognizable and return the response text. And also, together with the audio and MP3 type and the data that contain the MP3 audio base 64 format data. So let's check what has been done for convert PCM to MP3 function, which with the help of the PyDub library. This function first creates an in-memory WAV file, sets audio parameters, and then writes the PCM data. It uses the PyDub library to convert the generative WAV file into the MP3 and then encodes it in B64 format to be sent to Gemini for transcription. With this new transcription functionality, we now have the best of the both worlds. We get real-time audio feedback from the Gemini API and a transcribed version of that audio in our user interface, providing a comprehensive real-time response. You can see it in the demo how the application can show both the audio and its readable transcription at the same time. Now let's run the code. Okay, let's run the Python code to start the WebSocket server. Okay, your application running on port 9083 is available. That means our WebSocket server is running successfully. And then we should run our client. As you know, we have already designed an HTML client with the JavaScript functions in our previous videos. And for this demo, I have made some decoration on the styling without any other function changes. So you can find the source code in my GitHub repository listed in the description below. So let's run it by Python command, http server, under your project folder. So your application running on port 8000 is available too. So that means our client has been successfully running. Let's check it. When I open the web page on my localhost 8000, it shows a screen sharing request to let me choose what window or Chrome tab I want to share with the model assistant. So let me choose a research paper recently released, and then go back to the web page, click the talk button. Hey, what do you see on the screen?
I see a document on the screen. It appears to be a research paper titled, "Don't Do RAG, When Cache Augmented Generation is All You Need for Knowledge Tasks."
Can you describe some details about the diagram showing on the paper?
Sure, the diagram in the bottom right corner of the page compares traditional RAG and the paper's proposed approach called CAG. The traditional RAG diagram shows a series of steps, including a query being sent to a knowledge base, which returns a context. This context is then used alongside the query to generate an answer. The CAG diagram is more direct. The query directly goes to the language model, which utilizes cached knowledge to create the answer.
So when I'm moving down, I see a table called experimental result. So what's that table is talking about?
The experimental results table compares the performance of different models across different sizes on two datasets, Hotpot QA and Squad. It presents the results using top 1 and BERT score metrics. The table is organized by model sizes like small, medium, and large. Also, it shows results for different models like sparse RAG, dense RAG, and CAG. The table is designed to demonstrate how well each model performs on those benchmarks.
Okay, you heard the audio response and you see the text transcript. That's it. Feel free to leave any questions you might have in the comments below. Thanks for watching, and we will explore more Gemini 2.0 multimodal techniques in future videos.